this tells you what kind of scheme to use for different scenarios, right? So we have seen that if we use a centered scheme, because the resulting ODEs are marginally stable, even though it's a second order scheme, when you use it, you still get a lot of errors, right? Okay, but this is only true. This is only true when you have a pure advection. When you have a diffusion, we have not started looking at what kind of eigenvalues we get. So this is what we are going to be looking at today. So if we have a diffusion scheme, how would that affect the stability of our numerical solution? Okay, so let's start by writing down the second order derivative. So we have a second order spatial derivative, and last class we have did our Taylor series analysis and approximated the second order derivative at grid point n using un plus 1 minus 2 times un plus un minus 1 divided by delta x squared. So last lecture we did some formal Taylor series analysis to figure out, to derive the coefficients, right? If you ever forget the coefficients, you can derive it that way. At the same time, there is another, perhaps more intuitive way to figure out what these coefficients should be. And this is by writing down this in such a way. So this is a ratio between something and something. I'm going to write it as a ratio of ratios. Okay? I'm going to write it as the difference between first order derivatives divided by delta x. And this is going to be, well, delta x, and here I will have un plus 1 minus un, and here is un minus un minus 1. Do you see what I'm doing here? So here I am basically saying that, okay, the second order derivative theoretically is a first order derivative of the first order derivative, right? So why don't I just approximate it as a finite difference of finite differences? Okay, and so effectively, but I'm using a trick here. I'm not just strictly applying, for example, what I had in the last page. I'm not strictly applying, for example, the centered approximation. Because if you strictly apply the centered approximation twice, you expect to get a divide by 4 delta x squared, right, in the denominator. And in the numerator, instead of have un plus 1 and un minus 1, you would have un minus 2 and un plus 2. That would be kind of a waste of resources, because I did not use it's a less compact scheme. Right, I'm using kind of 2 grid points far away. And you can do Taylor series analysis and show that that scheme is strictly worse than what I have over here. What I have over here is that I'm taking a central difference, but always with half of the width as what I would be using if I were approximating the first order derivative. Right, so it is taking, if I draw a grid spacing here, so this is my n, this is n minus 1, this is n plus 1, right? And I have a certain function. I have a u as a function of axis here. What I'm saying is that I'm going to take the value here and approximate the first order derivative at this point using the slope between these 2 points. And then I'm using the slope between these 2 points to approximate the first order derivative here. I'm essentially adding 2 more grid points. I might call n minus half and n plus half, right? And this is actually the first order derivative. You can think of it as n plus half, and this is the first order derivative at n minus half. Now, how far away is n plus half and n minus half spaced? It's delta x, right? Exactly the same as delta x. So the difference between these is delta x, the difference between these is delta x, and the difference between the centers of these two is also delta x. That's why I have a divide by delta x here, divide by delta x here, and then divide by another delta x. This is another way to think about, although not as rigorously, right? You cannot actually, this way cannot, really, it's not a convincing argument that it actually approximates the second order derivative to whatever error. But it's a good intuitive way to think about it. I mean, usually you can derive schemes by thinking intuitively like this and then prove that it is what you want by doing Taylor series analysis.